Alright, everybody's back, so we can look at this example, which I think it seems more complex than it actually is. So you had a few minutes to think about this together with another couple of students. So what kind of ideas do we have in order to approach and solve this problem? So yes, basically this is exactly the approach that we have to use by looking at what we did before, which is basically one translating mass and one rotating object. Basically we know everything. We can theoretically solve any system that we see, of course, as long as we have we only have conservation of energy. So basically we need to exactly break this down in pieces, see what kind of motion is going on, and determine for each component what kind of potential energy we have, what kind of kinetic energy we have, and then once we have these pieces, we just need to put them together in the same equation that we saw at the beginning, T plus V equals constant, and then we just derive, and then basically we are done. So the hard part here is to identify what's going on in the system in terms of rotation and translation. Sometimes both of them occur at the same time, like this case here, because the disk is rotating at the same time the mass is translating. We need to identify the potential energy that we have. In this case, one is from the spring, one is from this shaft, and also identify what kind of kinetic energy. One will come from the translation of this mass in the horizontal direction, the other one will come from the rotation of this disk. So once we have all this, we are done. There is another thing that we have to pay attention to, and we need to make sure that we determine how many degrees of freedom we have in the system, because even if it looks like we have one translation and one rotation, which it seems like we have 2 degrees of freedom, in reality we have only 1 degree of freedom, because these two quantities, basically the rotation of the disk and the translation of the mass, are actually related to each other, because we said that we have the no slip condition between the disk and the mass. If we have no slip condition, it means that the rotation of the disk and the translation of the mass are related to each other. Since they are related to each other, these two basically constitute like 1 single degree of freedom for the entire system. Make sense? Alright, so now we can actually solve the problem. So this is the approach that we have to use every time we look at every time we want to use the energy method to solve, to find the equation of motion. So let's start with our principle of conservation of energy. So we have T plus V, we know that this must be constant. Right, so let's start by listing the kinetic energy. So as we said before, the kinetic energy comes from 2 sources, basically because we have 2 moving masses. So the first is the translational kinetic energy of the mass, and then we know that we can write that one as 1 over 2 m x dot squared. Right, we already have the displacement of the mass expressed with the variable x, and this is what the statement is asking us to find the equation of motion using the variable x. So this is already expressed in x, so we are good. Let's see what happens next. The next source of kinetic energy is the rotation of the disk. Exactly like we did for the pendulum, we can use the rotational kinetic energy. So we have 1 over 2 j, which is the moment of inertia, the rotational moment of inertia, times theta dot square. In this case, we are starting by using the theta as a variable, and then eventually let's see how we can relate x and theta. For now, we leave it like this. Next step, we need to look at the potential energy. So the potential energy, in this case, we have only one form of potential energy. In the previous case, when we were looking at the mass that was hanging from the ceiling, we had two forms of potential energy. One was the gravitational potential energy, and the other one was the elastic potential, so from the spring. Here, we only have the elastic potential energy because both the disk and the mass don't change their height, basically. Right. The mass stays in the horizontal, only moves in the horizontal direction, so doesn't move in the vertical direction, and the disk rotates around its center. So it means that the center of gravity is not moving up and down. It's not moving at all, actually, the center of gravity for the disk. Which means we only have rotational kinetic energy and no variation of gravitational potential energy. So when we write the total potential energy, we still have the two contributions. One is from the spring that is attached to the mass, so we can write 1 over 2 k2 x squared, because the extension or contraction of the spring is basically the displacement of this mass. And then we have to add the other potential, the elastic potential contribution, which is from this rod here. So we have 1 over 2, this is k1 theta square. Makes sense? Any questions so far? So we can basically now plug these two quantities in our principle of conservation of energy. So we have 1 over 2 mx dot squared plus 1 over 2 j theta dot squared plus 1 over 2 k2 x squared plus 1 over 2 k1 theta squared equal to constant. So now we can finally relate the two quantities that we have in this system. So we can relate the translation of the mass and the rotation of the disk. We said that we have the no-slip condition. So the no-slip condition means that for a certain rotation of the disk, we have a certain translation of the mass, and vice versa. So we can write this relation as x equal to the radius multiplied by the angle theta. We can also, of course, derive this expression, so we have that x dot is equal to r times theta dot. Which means that if we rearrange this one, these two, actually we have that theta is equal to x divided by r, and of course theta dot is equal to x dot divided by r. Now that we expressed both theta and theta dot as a function of x, we can actually plug here and here. So the expression becomes 1 over 2, and x dot of course will stay because this is what we want, plus 1 over 2 j theta dot, which is x dot over r, and it is squared, plus 1 over 2 k2 x squared plus 1 over 2 k1 x over r squared. And this is still equal to constant. I will put C here. Make sense? Alright, what should we do now? The exact same thing that we did before, which means we have to derive this expression. When we derive the expression, we obtain 1 over 2 m times 2 x dot x double dot plus 1 over 2 times j, and then we have 1 over r squared. This is still a constant for us, and then we multiply by 2 x dot x double dot, and then I will use the other line because I know it's not going to fit, so plus the third term, which is 1 over 2 k2, and then we have 2 times x and then x dot, and then the last term, which is 1 over 2 k1 multiplied by 1 over r squared, because this is still a constant, and then multiply by 2 x and x dot equal to 0. Now this expression has 1, 2, 3, 4 terms. We can actually significantly simplify this one because we can get rid of this and this, we can get rid of this and this, and also this and this and this and this, so all these 2's go away. And then also x dot appears in every term, so we can get rid of the x dot as well. And then we can go through this, when we go through this simplification, what we obtain is the following form. We have m x double dot plus j over r squared x double dot plus k2 x plus k1 x over r squared equal to 0. Of course, what we want to do is to bring our equation in the same form of the standard equation that we saw before, so we can put together the x double dot. So we have x double dot that multiplies m plus j over r squared, and then we can also put together the x, so we have k2 plus k1 over r squared equal to 0. And in the standard form, we have that the coefficient of x double dot is 1, so we have x double dot plus the ratio between this quantity and this quantity here, so we have k2 plus k1 over r squared and plus j over r squared times x equal to 0. We were asked to determine the equation of motion, which is what we have here, and the natural frequency. How do we have the natural frequency? Of course, we can look at the term that is the coefficient of x. So the natural frequency of the system would be square root of this quantity here, k2 plus k1 over r squared divided by m plus j over r squared. Make sense? Any question? So we were able to find the equation of motion by using the energy method for a system that otherwise would have been way more complex by using the force method. Alright, is there any question before we close for today? Alright, if there are no questions, I think we are done for today, and then we are going to meet again in a couple of days. Alright? Alright, thank you very much.